In this video, we are going to finish up talking the concepts in chapter 15. Now, one of the things that I want to at least discuss or establish is that NMR is not the only existing spectroscopy techniques. Previously, you guys have learned about the infrared or IR spectroscopy. And then after we conclude talking about chapter 15, we're going to learn about mass spectroscopy, which again, when it comes to mass spectroscopy, we will be looking at the mass overall of our organic compound. Now, taking this into account, if there are times when you're trying to define the particular structure of your molecule, these two techniques that I previously mentioned, IR and MS, may not be able to distinguish particular compounds from each other just because of the nature of what they identify. So let's take, for example, the three molecules that we have before us. These three molecules are going to be benzene rings that are disubstituted by methyl groups. As you can see, obviously, the substitution on the benzene ring is different from molecule 1 to molecule 2 to molecule 3. But overall, if we think about it, at the level of utilizing IR on these molecules, then the stretches that are going to be displayed on the IR spectra are going to be very similar for the three of them because all of them contain, for example, the carbon hydrogen stretches for aromatic compounds because of the presence of the benzene ring, or even if you have carbon-carbon bonds and then you see those stretches, again, because of the functionality or the functional group that is present in the three molecules, since it's very similar. IR will not be a technique in which we can distinguish all three of them. When it comes to mass spec, think about it. Mass spec is going to be looking specifically, just to give you a brief introduction, at the mass of the three compounds. They contain the same number of carbons, the same number of hydrogens. So for them, in this technique, there will not be a particular difference, okay? So having difficulty utilizing other techniques, this is why, as I mentioned in the beginning of this video series, that as an organic chemist, when you're in the laboratory, proton NMRs or carbon NMR are going to be one of the first resources that you utilize to elucidate a particular organic compound. Now, if we do the NMR spectroscopy, particularly the proton NMR for these three compounds, as you can see, and it is outlined in the bottom of the structures, each of them will have very distinguishable signals because the protons themselves in these three molecules are going to have different chemical equivalences. So for example, the first molecule will give us 3 signals in the proton NMR. The second molecule will give us 4 signals in the proton NMR, and the last molecule will give us 2 signals in the proton NMR. So understand that this is the reason, among many, okay, that protons NMR are so important when we're trying to elucidate structures. Now, understand that if we are analyzing the proton NMR for a molecule, there are several steps that need to be followed in order for you to determine the structure of the molecule. As you can see, I'm just going to mention the 5 steps and then I'm going to do a sample problem so you guys see them in action. So the first thing that we're going to do is calculate the degree of unsaturation. And the degree of unsaturation is given by the following formula. The degree of unsaturation is also known as the hydrogen deficiency index, or HDI. So if we're trying to calculate the HDI equals to half of 2 times carbon plus 2 plus nitrogen minus the hydrogens in our chemical formula minus the halogens, okay? So you can see X is for the halogens, N is for the nitrogens. As step 2, consider the number of NMR signals and integration. Then the integration can be given but also if it's not provided based on the number of signals, you can actually determine it. Okay? But understand that those two pieces of information, specifically the NMR signals, must be given. Now, understand that step 2 actually gives you clues about the symmetry that may be possibly found in the structure. Step 3, you have to analyze each signal and draw the fragments that are going to be consistent with each signal. This means that you will be drawing specifically the carbon atoms that are going to be containing the hydrogens based on the signals. Then you're going to assemble together the fragments into a complete structure. And number 5, we also have to verify our work. So you're going to verify that the proposed structure that you drew is going to be consistent with all the spectral data that we have. So in order to see this in action, we are going to practice with the following problem. The problem reads: the integrated proton NMR spectrum of a compound of formula C4H10O is shown. Propose a structure consistent with the data. So, as you can see, I have a little snapshot of the 5 steps that I just discussed. The first thing that we're going to do is calculate the HDI. So, I take my chemical formula, which I know is C4H10O, and then I say, okay, my HDI establishes that I'm going to take half of 2 times carbon, which in this case is going to be 4. So 2 multiplied by 4. Then I'm going to add 2. In this case, I don't have nitrogen. I don't have a halogen. So I just have to subtract the hydrogen atoms, which is going to be 10. Let me just make those numbers more clear. So it's 2 times 4 plus 2 minus 10, everything divided by 2. So when we do this, then we see that the HDI for our molecule is going to be 0. So understand that when we have an HDI of 0, this means that there is no degree of unsaturation. And what this means in the context of the molecule is that for this particular molecule, we're not going to have either cyclic systems or double bonds. As the values for the degrees of unsaturation increase, understand that that means that we're going to have double bonds, triple bonds, or cyclic systems. So at an HDI of 1, there will be a presence of a double bond or even a cyclic system. When we have HDI of value of 2, then most likely we're going to have either multiple double bonds or we can have a triple bond in the system, and so on and so forth. Okay, so as you can see, the next thing that we're going to do is consider the number of NMR signals and integration. For this molecule, we particularly don't have the integration, but we do have the signals. So when we look at the signals that are given between 3 and 4, we have a quartet, and a little bit past 1, we have a triplet. Okay, then we are going to analyze each signal and draw the fragments. Okay, so reviewing back into the information that we have been discussing, in step 3, this suggests that if I make these signals, okay, then the quartet comes from the idea that the neighbor is going to be a CH3. Okay? Because remember that in order for you to have a signal of a quartet, you need to have a neighbor that is going to be specifically going to have 3 equivalent protons. When it comes to the triplet, then this implies that for this molecule, the neighbor has to be possibly a CH2, okay? Because that means that if we have a CH2 as a neighbor, then again, according to the N+1 rule, then that's where the triplet comes from. Now, taking that into consideration, as you can see, we have an oxygen in the molecule. So for step 4, we need to consider, we know that we have a CH3 and we know that we have a CH2. So we already have 4 carbons in the system, so that will take care of 2. Now, taking this into consideration and knowing that we don't have any unsaturation in the system, the oxygen atom needs to be single bonded to these carbons, okay? Now, if we take this into consideration and we say, hey, if we have a CH2 and that is followed by a CH3, okay, that takes into account 2 carbons, 5 hydrogens, and the oxygen atom. Now, if to the other side of the molecule we draw a CH2 and a CH3, then not only representing this ether, okay, will make sense, but at the level of the structure, in a way, this kind of can be rationalized, okay? Because if I label these signals, and I'm just going to highlight them, this CH3, because its neighbor is the CH2, is going to be represented by the triplet here, that it is upfield in our proton NMR. This CH2 is going to be the quartet signal because its neighbor is a CH3, okay? And the integration, which is not given, but it could have given us a clue about it, is what will be the number of hydrogens specifically in the signal. But as you can see, for this molecule, we could define the structure without having the integration. Now, taking that into consideration, now we're going to verify the proposed structure, which was the explanation that I just gave. So for this NMR, this is the structure, which this is an ether and this is diethyl ether. So now we're going to switch gears and we're going to be talking about specifically carbon NMR, because it is the other type of NMR that we can take and is most commonly used in organic chemistry. So because protons, by far the most abundant isotope of hydrogens, proton NMRs are generally very strong. Now understand that when we're talking about carbon NMR, C13 only counts for about 1% of the carbon atoms in nature, because actually carbon 12 is going to be the most common isotope for carbon. So what happens in this instance is that, remember that carbon 12 cannot be utilized in NMR because it doesn't have the requirement of the odd number of protons or neutrons. So carbon 13 is the one that can be utilized in this technique. So understand that when we are doing carbon NMR, then we need a sensitive receiver coil and or concentrated NMR sample in order to run these experiments. Now, we already observed that in proton NMR, their shifts, their splitting and integration are important, but understand that in carbon NMR, only the number of signals and the chemical shifts will be considered. In carbon NMR, understand that the hydrogen and the carbon 13 splitting is often so complex that makes the spectrum unreadable. So when we are trying to utilize a carbon NMR to elucidate it, understand that This, we are going to be only observing the total number of carbon-13 signals. And the carbon-13 NMR generally is decoupled. What does this mean? That since carbon-13 is so low in the percent abundance for that isotope, the carbon atoms that are next to each other are not going to be splitting each other. So that's one of the difference between the carbon NMR and the protons NMR. Understand that in the vast majority of the carbon-13 spectra, all the signals are going to be shown as singlets. Now, when we compare proton NMR and carbon-13 NMR, the carbon-13 atoms require a different frequency of energy in order to make the spin flip, in order for the resonance to occur between the alpha spin to the beta spin and back. So understand that we are also utilizing an internal standard, okay? And compared to the standard TMS, then the carbon-13 NMR signals generally appear between 220 and 0 ppm. So understand that we also are utilizing that internal standard. Now, each signal in the carbon-13 NMR spectrum represents a unique type of carbon. So when we have a structure, understand that planes and axes of symmetries can cause carbon atoms to be electronically equivalent. Now we are going to be looking at an example of how that happens. So as I was mentioning, whenever we have molecules and we're considering the carbon NMR, we have to think about symmetry in order to know the number of carbons that can be displayed in the carbon NMR. So again, we are going to be utilizing that di-substituted benzene molecules that we introduced previously. Now, we just established that if we had those molecules, again, the dimethyl groups that are substituents in the benzene, the proton NMR will show different signals. Now, if we did a carbon NMR on them, also there will be different signals appearing in the system. So, as you can see, due to symmetry, for example, the first disubstituted benzene, which has the methyl groups in carbon 1 and 2, okay, because we're going to have an axis, and if we fold the molecule in half, okay, the right and the left look alike, that one is going to show 4 signals. If we look at the disubstitution at carbons 1 and 3, understand that for this signal, similarly, if we see as an axis the middle of the molecule, specifically for this one, we are going to have 5 signals. And then for the last one, we actually have to look at 2 axes, the one that it is vertical and the one that is horizontal, and we will see that in this case there's going to be 3 signals. Okay, so understand that whenever we're dealing with molecules, we need to look at the axes and planes of symmetry in order to know the different carbon atoms that will be present in a carbon-13 NMR. Now, like proton signals, there are chemical shifts for carbon-13 signals. Now, they are also affected by shielding and deshielding, and as you can see, this is slide 62. Here we have the different sections or the different regions in which we can see these functional groups on carbon NMR. So this is a very useful chart whenever we are doing analysis of a particular carbon-13 spectra for a molecule when we're trying to look at the different signals. Now, Understand that carbon-13 spectra generally give singlets that do not provide any information about the number of hydrogen atoms that are attached to each carbon. Now, if a depth 13 experiment is performed, and depth stands for distortionless enhancement by polarization transfer. That's what depth means. Experiment, then understand that this NMR experiment provides information about the number of hydrogen atoms attached to each carbon. So understand that in order for this technique to work, you are going to do, in essence, 3 different experiments to gather all the data. So the depth carbon-13 experiment actually has 3 stages. Okay, stage number 1, you're going to run just an ordinary broadband decoupled spectrum, so the regular carbon-13 spectrum. On the second experiment, you're going to run a depth 90. And as you can see, the depth 90 experiment is going to be used under special conditions, and is only going to show us the CH carbons. Okay? In a depth, then the third stage of this experiment will be a depth 135 experiment that, again, utilizing conditions specifically for that type of experiment, you are going to be looking at the CH3, okay, and at the CH, and understand that those are going to show positive signals, which we will see in the following slide. And then if you have a CH2 signal, that is going to be shown as negative. Let's actually see how this is illustrated. So in table 15.4 in the textbook, you can see at the shape of the signals, specifically when it comes to the depth carbon-13 spectroscopy experiment. Okay, so as I mentioned, there are 3 stages that need to be done in order for this experiment to work. The first one is the broadband decoupled, which is the regular C13 NMR. Then we have depth 90 followed by depth 135. And as you can see, for the regular broadband decoupled, we're going to have singlets. Okay, depth 90, as I mentioned, because the signal is going to be specific about the CH. That's why you're not going to see any CH3s or CH2s or just the carbon atom, only the CH, and it shows up as a singlet. When we do a depth 135 experiment, as you can see, the CH3 and the CH are going to show up as a positive signal. The CH2 is going to show up as a negative signal. That's why the singlet is pointing down, and the carbon just by itself is not going to be appearing. The last thing that I want to mention when it comes to NMR is that there's actually real life applications, more than just looking at specific organic compounds. Maybe some of you have, because of medical reason, have had to have a magnetic resonance imaging or an NMR, or you know somebody, or maybe you work at a hospital and you know of this technique. Understand that an MRI is a magnetic resonance imaging, okay? And this instrument are essential for looking at parts of the body. If we look at it at what an MRI machine is, it is essentially a proton NMR spectrometer. Now, the body in this instance is going to be analyzed as a whole rather than in a sample like we do in the laboratory for organic compounds. Understand that the different tissues, because they have different concentration of protons, they are going to be illustrated in the images, and the MRI overall gives us a 3D image of different tissues. Now understand that in here the radio waves and magnetic fields are very mild, so there's no side effects experienced by the person.